Hello there and welcome back to Steamer with Steve. Today we're going to keep going on with our coding battle experience. We're going to do the Logic 2 exercises. So let's just jump on in here. So coding bat logic number 2, and we've got some medium Boolean logic puzzles here. So they're a little bit trickier, but shouldn't be so bad. So we've got 1, 2, 3, 4, 5, 6, 7 of these to do. So we're going to start off with the make bricks option. And here we go. So we want to make a row of bricks that is goal inches long. We have a number of small bricks, 1 inch each, and big bricks, 5 inches each. Return true if it is possible to make the goal by choosing from the given bricks. This is a little harder than it looks and can be done without loops. So to start, let's just do the brute force attack with this. Okay, so we're going to go 4i in range of big bricks, and then go 4j in range of the small bricks. If the small plus the big times 5, if that's all equal to the goal, snaky bite, return true. So that will go through every single possible combination of the big bricks and the small bricks over and over and over until it finds the goal. And if it does, it returns true. Otherwise, it returns false. And I can't smell. Small, sorry. Right, so it's timed out. So what I suspect's happened down here, it's done it too big. So what that means is basically it's timed out because the operations were, the memory that was allocated to this program wasn't enough to go through and do every single iteration. And that was sort of hinted here with if it looks a little harder, can be done without loops. So we're going to try and do this with some if statements instead. So we want to check. What do we want to check? Let's check to see if we can actually, we've got enough bricks if it was the worst case scenario. So if we just literally went, if the small bricks plus the big bricks times 5, if that's less than the goal, let's return false. Right? And if that is real good, let's return true. Let's see what we get from that. Oh, cool. So we got more than half the test correct just by doing those statements. Okay, so do you see how that's filtered it through? It's checked to see that if we do the small plus big times 5, if that's less than the goal, we can't do it. So to stop. So let's have a look at this error 1. So in this case here, we had 3 small bricks and 2 big bricks, which would mean that we could use 13 bricks, and we need 9. And what it's assumed is we've gone past 13, so it's all good. Let's return true. But the problem with that is there's 3 small bricks. So to make 9, you can't just chop one of those big bricks into fifths and have 4/5 of the brick and put it in, right? And then similarly, you can't use 1 big brick plus the 3 bricks because that only makes 8, which doesn't reach that limit. So we want to check the mod of this, it looks like. So we want to check if we mod the out of the goal by 5, if that's greater than or equal to the small bricks that we have, then we're all good. So let's go if we do goal mod 5, and the base case we've got here is return true. So we want to do the opposite. We want to see if that doesn't work. So if goal mod 5 is less than how many small bricks we have, it's all bad. So it's be false. We would return false. So if in this case here we did 9 mod 5, which gave us 4, right? So 9 mod 5 gives us 4, and 4 is less than 3, then we return false. So that shouldn't work. So let's see what happens now. Okay. Sorry. Greater than small. My bad. I was right the other way around. Right. So because the goal was greater, right? So that bit there was greater than the small. Sorry, I had the logic backwards. It was all good. Cool. Next one. Lone sum. Given 3 integer values, A, B, C, return their sum. However, if one of the values is the same as the other, it doesn't count to the sum. So 1, 2, and 3. Let's just do a filter on this guy. So if we go if a, so hang on, return the sum, however, if one of the values is the same as the other, it doesn't count. So if we got 1, 2, 3 gave us 6, 3, 2, 3 gave us 2 because 3 is equal to 3, and then 3, 3, 3 gives us 0. So if a is equal to b, so if the first one equals the second one, we're just going to return c. If a is equal to the last one, so it's equal to c, we return b. If b is equal to c, we return a. And then otherwise, we'll just return them all added together. So a plus b plus c. See how that goes. Oh, cool. And then the base case as well. Sorry. So back up here, we go if a is equal to b, and I'm pretty sure in Python this will work. So if they all equal, just return 0. Now that's pretty cool. Bit about Python is that it allows you to do that. Most programming languages you need to write a separate statement like that. So because you can only compare two variables together. You can't compare multiple things like that in a row, but that's one of the benefits of Python. Cool, next one. Given 3 integer values, a, b, and c, return their sum. However, if one of the values is 13, then it does not count towards the sum, and values to the right do not count. So for example, if b is equal to 13, then both b and c do not count. So 1, 2, 3. We'll just do an overriding thing with this. So let's think this through. So if a is equal to 13, b and c don't count. They all equal 0. Every single value equals 0. If b equals 13, a, depending on what a's happened, but we've filtered it already, we've checked if it's 13. So we can assume at this stage in the program, a's all good, we're up to b. If b is equal to 13, b and c equals 0. Otherwise, it's all good, carry on. Then the next one's the last bit. If c is equal to 13, c equals 13, means that it's 0. And then you're done. So it's just a straight if statement. So if a is equal to 13, snaky by it. A just becomes 0. B equals 0. And C equals 0. Cool, so that's the first layer of the filter. Next one then is if B equals 13, snaky by it. B equals 0. And then C equals 0. And then the last one, if C equals 13, snaky by it. C equals 0. Cool. So then we just literally add them all together. Return A plus B plus C. Cool. Done. So do you see how that's just filtered it through? Let's just check to see if they were equal to 13. If they were, just make them equal to 0 for all those. Next one, given 3 int values, A, B, C, return their sum. However, if any of the values is a teen in the range of 13 to 19 inclusive, then that value does count as 0, except 15 and 16s do not count as teens. Write a separate helper function, def fix teen, n, that takes in an int value and then returns that value fixed for the teen rule. In this way, you avoid repeating the teen code 3 times with so no decomposition. So having to rewrite the same bit of code over and over is annoying. Define the helper below and same indentation. So let's define that function first. So we're going to define fix teen n, snaky by it. And what we want to do is check if that's in the range of 13 to 19. However, if it's a 15 and 16, they're all good. They don't count as teens. So let's check that first. So if n is equal to 15 or 16, n is equal to 16, snaky by it. Let's just return n. Yeah. So if it's 15 or 16, it's all good. Carry on. If n then is in the range from 13 up to 19, which we'll type in 20, snaky by it, we would then return, what did it say, a 0. So even though 15 and 16 exist inside of this is a nicer way of doing it because this allows for scalability. Because let's say it was up to 199, I can just type that and then it does it. Another way is that you could have written it like this. So you could have gone n is equal to 13, n is equal to 14, n is equal to 17, n is equal to 19. Or you could have done a list. So you could have written a list here. So you could have gone square brackets, what was it, 13, 14, 17, 18, 19, right? So if it's in that range with those, that's all good, but I just like that because it's just nicer. Otherwise, it's all good, just return n. So back up here, we're going to go return 16. I'm going to go a plus 16 of b plus 16 of c. Let's run that, see what happens. Yeah, nice. Cool. Next one. Round sums. For this problem, we'll round up an int to the value of multiple of 10. Is the rightmost digit is 5 or more, so 15 rounds up to 20. Alternatively, round down to the previous multiple of 10 if its rightmost digit is less than 5, so 12 rounds down to 10. Given three ints a, b, c, return the sum of their rounded values. To avoid code repetition, write a separate helper function, def round 10 num, and call it 3 times. So let's go down here. We'll go def round 10 of the num. Snaky bite. Whoop, didn't spell that right. So we'll go round def round 10 num of num, and if the number mod 10, so we're going to get the back end, so it's going to either be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you had, I don't know, 214, it'll give you the 4. So if that is less than 5, because that's how we round, we wanted this thing to return, let's think this through. We want to return the number either above or below it, so in groups of 10. So if it's 44, it should go down to 40, not the, and chop off the 4. Let's do that then. So you could either do integer division or you could do this. So I'm going to do num minus num mod 10. Right, so then that's going to literally cut off the tail here. So let's just try that. Return round 10 of a. Yep, so 12's worked. 4 gave you 0, 20, 23. Yep, cool. So that's rounding it down. Otherwise, if it's not that, we want to return that thing up here, plus 10. So we go num minus num mod 10 plus 10. Now, just so that we force it to do this bit here first. No, we don't actually really need to. Because that's just going to be a value and then adding on 10. That should be work. Let's give that a go. Where's the number that's bigger? 16. Yep, that ran up to 20. Cool. Awesome. So that now should work. So then we can go round 10 of B plus round 10 of C. Cool. Done. Next one, close but far. So given three integers a, b, and c, return true if a, b, or c is close, differing from a by at the most 1. Right, so if we got a, we look at b, and then we look at c, and seeing if they're at least 1 away from each other. And while the other two, so other combinations, are both true or more, we can use the abs function with num, which computes the absolute value of the number. So we've got two different things. We want to check first if the absolute value of a minus b, if that's less than or equal to 1. We then also want to check down here if the absolute value of a minus c, if that's less than or equal to 1. So if the first compared to the second is less than 1, and then if the first is compared to the last is less than 1. If that's true, then we want to check to see if the absolute value of a minus c, so if the first two are close to each other, we want to see if the first and the last are far away. So we want to see if they're greater than or equal to 2. And the absolute value of B minus C is greater than or equal to 2. So if that's all true, we return true. Okay. Then pretty much the same pattern down here. So then we want to check to see if the absolute value of A minus B is greater than or equal to 2, and the absolute value of B minus C is greater than or equal to 2. So if that's all true, we then return true. If it's not, we come down here and we just return false. Line 7, snaky bite. Sorry. We've got snaky bite there, and we need to put a snaky bite on the end there. Cool, done. Next one, make chocolate. Now this one's a bit tricky, it looks like. Last one. Yeah, so we want to make a package of gold kilos of chocolates. We have a small bars, 1 kilo each, and big bars, 5 kilos each. We need to return the number of bars, return the number of small bars to use, assuming we always have big bars. Before small bars, return -1 if it can't be done. So if we got 4 and not 1, you only need the 4 bars. So you just literally just have how many bars there were. If you have 4 then 1, you're going to be out, so you can't, that's not going to work. In this case, you only needed 2 of those 4 bars, so you didn't need all of them. You only needed the ones that were left over, which was this bit here. Rightio. So let's think this through. If what we're thinking, if the goal is less than or equal to the big times 5, so that means that the goal, so we want to make 9, right? So if the goal is less than or equal to this bit here, right, the remainder, however many we've got to make up. So in this case, 1 times 5 gives us 5, so 9 is less than or equal to 5. Yep, that's true. So then we need to have however many we've got to make that up. So we would do the goal mod 5. Yeah. So if the goal is less than or equal to than that, we just literally have the remainder that we need to do is equal to the goal mod 5. Because that's how many of those are needed to get it across the line. So here's the goal. We wanted to make 9. We did big, so we did 1 times 5. That was if that's bigger, that's all good. Then we need to work out how many of these left over will go. So this case here, let's think of it if it was 9 and 2 there. Right, so 2 times 5 is 10. The goal is less than or equal to 10, that's true. So therefore, we'd only be worried about how many of these we've got to make up to get to the remainder. The other side of that, then, is we want when it's not bigger. So if the bigger one, like what we've got here, is we just want to have the remainder that needs to be left over is equal to the goal minus 5 times the big. Yeah, and then that will tell you how many of these little guys that you need to fill that up. Okay, so there's 2 choices here. The goal is either greater than the number of bigs times 5, okay, which will then give you this bit here. So the remainder would be whatever this bit here would be left over. So previously when we had this is, I don't know, say we had to find this where we had, I don't know, 2 bars. So let's say, 2 bars, we had 1 big bar and we had to make 8. Right, that's obviously not going to work because it's 7. But if I did that, that also shouldn't work as well, right? So it should say that it's not possible. So we need to have something then under here to check that. So if the remainder that we've just worked out, if that's less than or equal to the small, because there's only two different ways that can either happen. You either don't have enough big ones or you do have enough big ones. So if that is less than or equal to small, you just return the remainder, right? Which would be that number. Otherwise, you just return nothing. So you're going to return no codes. Whoop, and then we forgot the snaky bite there. So snaky bite there and there. Let's see how that goes. Cool. So hopefully that makes a bit of sense. There's a little bit trickier one. So literally, if the goal is less than or equal to the big times 5, right? So the end game here, you had to build 10, right? But you had more bigs, right? You would just do the goal %5, because then that would tell you how many of the little ones that you need to make up to get to the end goal. Otherwise, you would just do the remainder is equal to the goal minus the 5 times the big, because then that would tell you how many you're away from it. And then if the remainder is less than or equal to the small, so however many you worked out from these two options, if that's less than or equal to the small, you just return the remainder. Otherwise, it's all failed and you just return -1. So hopefully you've picked up on how to use this coding back examples. Lots of fun. They were a little bit tricky, particularly that Make Chocolate one. But yeah, hopefully you've enjoyed. Thanks again. Don't forget to like and subscribe down below, because that does help with our YouTube algorithm. And see you next time on Steam It with Steve. Adios.